Hello, my name is Lakshmi. Now I would like to explain about three laws of Kepler. Okay, let's move to the first law of Kepler. The planet is not going around in a perfect circle, but it going in an ellipse. So, an ellipse is like a squashed down circle, but as we know that the circle has center focus, like this here. An ellipse has two foci, this and this. We say that has an eccentricity of 0. The circle has an eccentricity of 0, but when we stretch it, the eccentricity will increase up to the maximum of 1. If we stretch it, it will be like this. The eccentricity increases too. Most of a planet has the eccentricity of something anywhere between 0.01 and 0.1. So there isn't a great level of eccentricity, and for all intents and purpose, we could almost consider that the planet orbits as circular, but they are actually ellipse. So the first law says as the planet moves around in an ellipse where the sun is one of the foci point. Here, the planet, this is the orbit and this is the planet. Then along comes number 2. The fact here is the planets are moving faster when they are around the closer edge. Here, the closer edge to the sun. And when they are farther away, going here, it will be slowest. And then what he was basically saying is that if you have two given areas of the sectors of the ellipse, and if there are is exactly the same, then the time of travel between those two from here, from this one, is the same. Like, since the radius here is smaller, it makes sense if the planet is, in this case, is traveling faster than this side, and it travels slower over this side. So this is planetary law number 2. Planetary law number 3 actually looks at the relationship between various planets around the sun, and in fact, the planetary law of motion number 3 is basically true for any particular object revolving around a central body. Although there are many planets, but we can do the same concept of Kepler's third law. But what is Kepler's third law all about? Before that, we need to understand that we have a number of measurements here, and we work out this radius here to distance here. What we call r, we usually revert to useful to call the semi-major axis of its orbit, so we call it R1 over here. This R1, and over here we have R2. So we have two radius. Now clearly this radius is smaller than this radius. This radius is smaller than this radius. When the planet going around the sun will have a particular period, and it called T1. This here and here, T1 and T2. T, or period, is the time it takes to go around one loop for this planet. It is equal to T2. T1 is equal to T2. And we know that there's going to take longer, but easily of the understanding the fact that it has to travel a lot farther, and so Kepler from many years played around with the numbers that he had available to him to work. Is there a relationship between this called variable, and he worked out this. He said if we have the radius of the first one and you cube it, like radius of the first one, and we cube it, and we divide it by the period of the first one and square it, that value is the same if we do this for another planet, object or satellite in this orbit. It's the same, like R2 cubed and D2 squared. So there is a constant relationship between the cube of the radius and the square of the orbit. If we look out another planet in this particular of the sun, work out its period, work out its radius, then the relationship between the two argued over t squared is a constant value. Is the same for every particular planet revolving around a common body, which is the sun in this case. If we increase the radius, the period also increases, but as we can see, it does not increase at the same factor. It's the cube of the radius and the square of the period that gives us the mathematical relationship, and he established that is constant, but of course what Kepler wasn't able to do is explain why it is a constant. Because of Kepler cannot explain why is it constant, then Newton provide an explanation as why it is the case. First, we need to understand, of course, is that Isaac Newton was responsible of our understanding of law of gravitation, which is that the force of gravity between any two objects or more is equal to the gravitational constant multiplied by the product of the second mass, the two masses divided by the distance between the square. A planet that is revolving the sun also undergoes is not only gravitational but undergoes circular motion. So what we have is that the planet going around a circular motion has a centripetal force. That's all from me. Thank you.